Now I'm going to make a video about how I made all this happen. Especially the anemometer. The digital wind vane I sort of did before. But that's fairly easy. This is much more complex. So if you're interested in seeing how it's made, keep watching. So I'm going to work everyone through the schematic of this and how to design something like an anemometer that works in for a low frequency signal, such as a spinning anemometer. So the way generally we want things to work is that we have the spinning anemometer. It's basically on a shaft, and you got 3 little cups, and they're facing in different directions, and you want it to spin in the same direction, and so in this case it's going to be spinning this way. I have attached to it a Hall sensor. It's an A3144 Hall sensor, and the way this works is it's basically a Hall sensor is a magnetic sensor. The A3144 kind of looks like this, and it's got 3 pins. It's got a VCC, it has a ground, and it has the output signal. And what the output, the way you connect it is you connect the output via a relatively large resistor to VCC, and it gives you, let's say this is a 20K resistor I used in this case, and it keeps the signal high. And every time there is a magnet sensed next to the Hall sensor, what happens is the signal, which is high, if I was going to graph it out, gives you a low pulse. So every time there's a magnetic sense there. So what I did to start the master signal to start the process, and I think I described this in my Hall sensor video, is I put the output signal through an inverter, and so that gives you a signal that looks like this. It's a very short burst every time the magnet on the spinning anemometer faces or touches or comes close to the Hall sensor. And so what this basically gives you is this is the period of rotation. Now, the problem here comes in when you try to measure this frequency. So when I initially designed this circuit, I thought it was going to be very simple, very straightforward, and very easy. And so what I did was I just attached this signal and plugged it into the clock of a CD 40110, which is basically it's a counter that also controls an 7-segment. So there's a 7-segment LED display driver, and what it does is it just connects to 7-segment LEDs, and it gives you a reading of various numbers that you get from this. So I figured initially is all I had to do was use my frequency counter that I designed in a separate video and basically count this, and whatever number of pulses are sent to this counter, in a 1 second frequency measurement, which is hertz, it would give you a rotations per second measurement. And that was all well and good, and that's all well and good to calculate frequencies that are fairly high, and like a spinning fan or a spinning motor or something like that. But what I realized very quickly was when the anemometer was spinning, it was spinning at a maximum of average of 1 rotation per second, 2 rotations per second. So even when I was spinning it really quickly, I would get to 3 or 4 rotations per second. So and the resolution of this kind of signal is not that good, because when you translate this to RPM, this translates to 60 RPM at 1 rotation per second, 120 RPM at 2 rotations per second, 180 RPM at 3 rotations per second. And so that's what I would get. I would either get a value of 0, 60, 120, or 180. And that's not really good enough for a low frequency signal. And as I've discovered, to deal with a low frequency signal like this, to get a better resolution on it, it's better to actually measure the period of the rotation. You make something called a reciprocal frequency counter. So what we do with that is basically, rather than measuring the rotations per second for something that spins at a maximum of 3 hertz, 4 hertz tops, or even less than 1 rotation per second, what you do is you count the amount of time that it takes to make a rotation. And so rather than getting hertz, what you're getting is a value in time units. So what I did next was I created a period counter. You can see that in another video as well. And so what I did was I had this signal, rather than going to a counter, instead I had the inverted signal, same inverted signal, which looked like this. And what I had it going into was a flip-flop, a T flip-flop. What that T flip-flop did was, every time a signal came in, the flip-flop would go on. And then every time the next signal would come, the flip-flop would go off. And so with period, I would have my flip-flop response would be something like this. And it was gated with these signals. So with that happening, I had the flip-flop attached to the base of a transistor through a 1K resistor. And into the collector of the transistor, I would have a 100, I would connect a 100 hertz clock. Basically, this was a 555 timer that I had set to oscillate at 100 hertz. And so what that did was, and then obviously this part went through a 20K resistor to ground, and the output would come from the emitter, and that I sent into my counter circuit, my CD40110. And the results of this would give me the time of the period of rotation. And it was a fairly accurate time, and this was measured in 1/100ths of a second. Basically, if this rotated at less than 1 second, or 1 second or 1.2 seconds, I would be able to get that measurement fairly accurately. Now, the way to get a nice high resolution reading from a reciprocal frequency counter is now after you get the time of period of rotation, then you have to calculate, and if that time period is equal to t, then the frequency of rotation is equal to 1/t. And that gives you rotations per second, or rotations per second, to a much to a much more precise reading, to a much more precise value. Now, to get from this value to rotations per minute, you basically have to, since we used hundredths of a second, just have to calculate how many hundredths of a second go into a minute. Well, that's 6,000, right? So to get rotations per minute, frequency and rotations per minute, that would equal 6,000 over t. Now you can make this as precise as you want. You could put 1 kilohertz clock there. You could put 1 megahertz clock there. Whatever you have to do in order to get the precision that you want on the reading. So let's say, for instance, the rotations per second, let's say it rotated, it took 0.1 seconds to make that rotation. If it takes 0.1 seconds to make that rotation, then I would get 1/t, which is 10. And if I would do 6,000, if I would rotate to get rotations per minute, I would do 6,000 over 6,000 over 0.1, or 6,000 over 10, and that would give you a rotations per minute value of 600. Now, this thing is never going to rotate at 600, but let's say it did. Let's say it rotated once every half a second, 0.5 seconds. It made the rotation. So 6,000 over 0.5 seconds, or over, if it took 0.5 seconds, that would be 500. So 6,000 over 500, and you get a value of 30. So, you wouldn't have to be stuck to these values of 0, 60, 120, 180, and that's the benefit of using a reciprocal frequency counter. Now, this math is really, really easy to do if you use the microcontroller, but in the spirit of what I'm trying to build here, I don't want to use a microcontroller. And so the entire thing has to be done in analog, or with, digital chips, but the entire thing has to be done with just integrated circuits. So and this took me forever to figure out because measuring a period is easy, that I accomplished here. But how do we take this value, t, and do 6,000 over t in order to get your RPMs using just integrated circuits? And that is what took me forever to figure out, especially because I'm not an engineer and I don't have any experience with this. And I didn't want to just settle for using a microcontroller. So I had to design another circuit to do this, and I'm going to describe it to you guys here. So, so the way it all starts out is you have your inverted Hall sensor, and this is giving you a reading like this. Sometimes it varies, and the period varies, and so this distance is all the period. Let's call it T, since that's our that's the time of the period. So what I started with was I needed something that set off several different counter stages in separate different stages. So what I wanted to do was count the period using a 100 hertz clock. Then I wanted to take that period value, T, and stop counting the period and do a separate count where I would do 6,000 divided by T. And so what we would have to do here is we would basically have to see how many times that count T goes into the number 6,000. Well, so what I figured out is the way to accomplish this is once you get that value T, you stop counting and you put that value into some kind of into a place where it's stored, something presettable that also down counts. So you put it into a down counter, you put T into a down counter, and then once you have that down counted T in the down counter, then you start a separate clock, a faster clock. I used an 18 kilohertz clock, all with a 555 timer. And you just make this count down repeatedly at the same time as this same clock causes an up counter to count to 6,000. When this value reaches 6,000, I then wanted this down counter to stop counting. The output every time the down counter reaches 0 is basically 6,000 over T. And that 6,000 over T value goes into the ultimate CD 40110, and that gets displayed on an LED display, 7-segment LED display. So, how do we implement this? So I started out with the brains of the operation, which I've shown in a separate video, but basically I used a CD 4017 counter. This is a decade counter. The pinout of this you could see here, but basically this is ground. To VCC, what I did was I wanted it to have a power on reset. So every time I powered the whole system on, I would have a 0.1 microfarad capacitor here, and the other side to a resistor that went to ground. And so every time it would turn on, it would reset to the 0 value. And so here you could see 0, 1, 0, 1, and 2. So the inverted Hall sensor, this signal would go to the clock input. which is pin 14 here. Okay, so what that would do is if you take the outputs of this, and you could see Q1, Q0, Q2, those are the outputs. And so when you first turn on the counter, it would be at the 0 state. And that is the quiescent state, and that's the starting point. That's where it all starts out. Okay? When that first signal from the Hall sensor comes in, this gets clocked and counts up to Q1. Now, at Q1, this is the stage at which I wanted to start counting. So let me put this away here. And so what that would do was that would send the signal to a period counter. Same way we drew out the period counter before. 1K resistor here goes to the base of a NPN transistor. This NPN transistor is I only used 2N2222 transistors. And I'd have this gating the period count. So the input to this would be a 100 hertz oscillator, 555 timer, right? That would be sent through a 20K resistor to ground. And then the output from the emitter would go to our count. And so for this portion of things, I needed to use a binary counter, not a decade counter, not a BCD counter. And so ideally I would have liked to use an 8-bit counter, but I ended up getting access to multiple 4-bit counters. So the counters that I used is a CD 4029. So let's draw that in here. And these are CD, actually I'll draw it here, CD 4029, CD 4029. And so what this did was I have what a CD 4029 pinout is. And basically it's a 4-bit binary counter that's cascadable. And the key is that it's presettable also for the down counter portion of it, not so much for the up counter. It doesn't really have a reset signal, which is a little bit annoying, but you can cascade them, so that's good. And these could be, you could count up with them, you could count down with them, you could either count in binary or BCD. And you could preset them with the jam 1, 2, 3, and 4 for the bits 0 through 4, 1 through 4. And you could cascade them because they have a carry out and a carry in. So we move that. So the way I would do this is I would send the output to the clock. Okay, and it would basically clock both of them, so it would be connected since they're cascaded. The carry in of the most significant bits area here would be connected to the carry out of this one. Okay, and and every time all the presets I would connect to ground, and so let's call them J1 to J8, since there's 8 total, to ground. And so it could be resettable. And then what I would do is I would get, every time the period would count, every time this was, Q1 output was high, you would get a period count that looked like this. As soon as Q1 would go off, it would stop period counting. And so you'd get a tracing that looks like that. And so the range here with two cascaded 4-bit counters is 8 bits, which is 0 to 255 in decimal, right? So what that would do is it would count while Q1 was on. As soon as the next pulse from the Hall sensor would arrive, it would turn that off because it would go to the next one, Q2. So in that way, it would measure during that time in between the first pulse and the second pulse, you would get a signal of, you'd get a total count of the number of 0.01 second pulses that occurred during that period. So you would get a value of the period in hundredths of a second for the duration of that entire period. So now, once we have that, then the next pulse arrives. What I wanted to do at this point was now perform this function. And so this function, the 6,000 over t, to get the true RPM in a more precise fashion, I would need to send this value to the down counter. And so what I did was I basically took the outputs of this, Q1 through Q8, and I attached them to the J1 through J8 of a completely second set of CD 4029s. So to do this, all we had to do was the preset enable pin on the CD4029, which is pin 1, and they're interconnected, is when Q0 or when Q1 goes off, the falling edge of that signal, the falling edge of sorry, let's put this to here, triggers this to get preset with the final period count. And once that's done, now we needed to start counting down. So the clock signals, which are interconnected here, clock, this is being clocked by a fast clock. That's going to be the 18 kilohertz clock. So I had this set up as another 555 timer. I tested it out in the circuit to make sure it was accurate. And what I did was, this is a 555. basically, this is wired in astable mode. To make an 18 kilohertz clock, I basically pin 1 went to ground, pin 8 went to VCC. Then from VCC to the discharge pin, I had resistor, then another resistor to pin 6. Pin 6 is connected to pin 2. These resistors were both R1, R2, equaled to each other, and these were 2670 ohm. Okay. Then pin 2, I had a capacitor, C1, going to ground. And this capacitor was 10 nanofarads. And that gives you an 18 kilohertz clock. So the only thing is that I didn't want this clock to be constantly counting. So there's the master reset pin, a pin on the 555 timer that's not often used. And this pin, in order to start the clock, has to be high, and as long as that pin is high, it is inactive. It's not resetting the count. It's not resetting the charge-discharge cycle. So this is an active low pin. And what happens is I have this via a 20K resistor tied to ground so that the clock is not active in its quiescent mode. And then what happens when Q2 goes on, and so I have Q2 connected to here. As soon as Q2 goes high, this asserts the value on pin 4 to be high and allows the clock to start. When Q2 is not on, this is tied to ground. It's pulled low by this 20K resistor. And so because of that, this now starts counting. And this starts counting down. Now, the outputs, let me just write this, see, carry out, carry in. So the output of the second CD4029, the most significant bits, that will give you the final value, is the carry out. So this carry out of the second chip basically carry out is usually high, and every time the down counter reaches 0, it gives you a negative going value. And so to reset this to start counting again to the same preset value, since these values are still in here, the Q1, the period value is still inside these chips, all we have to do is provide another positive going signal to the preset pin here. And so what we do is we take this signal, we put it through an inverter. And for an inverter, I just used a transistor-based NOT gate. It kind of looks like, I'll show it later, but it kind of looks like a fairly commonly used transistor NOT gate. We put it through an inverter, and we get a a signal like this. And that signal we have feeding back into here, and it resets it again. It presets it with the same period count value, and then the count begins anew. Now, how do we know? Because this will count indefinitely. So how do we know when we've counted 6,000 times total? And the way to do that is by having a separate counter that counts to 6,000 and have that feed back and stop this clock again. So the way I did that is I'm sure there are easier ways to do this, but I used more CD4017 chips. So I had a total of CD4017 that were cascaded together. Here we go. I'll draw them all out. Times 4. And so this clock also was attached to the clock signals of the CD 4017. It was actually attached to the first clock. And then I had 4 of them cascaded together. These all are decade counters, so they count from 0 to 9 or 1 to 10, basically. And so the carry out of this one went to the clock of that one. Carry out of this one went to the clock of that one. The carry out of this one went to the clock of the final one. Now, back to the decade counter. So when this value reached 6,000, the output for the number 6 on this chip, Q6, was very important, because when it reached when this value would reach 10,000, this would be the only time that this would ever reach 6,000, is when this pin went high. Otherwise, it's low for the entire count. When this pin goes high, this is when we know we're done counting down. And when we're done counting down, we have reached the number of times that we've counted down total, because this carry output signal is the final result of this equation, of this fraction, 6,000 over t. This gives us a train of pulses that are, every pulse here is one time that this has counted down from the period value to 0 at this rate of 18 kilohertz. So what this value is our final value. It's the answer to the question of what is 6,000 over the period length in hundredths of a second, and that gives you the RPM value. And that is the final value that goes into our cascaded CD40110 LED display drivers. And we have a value of RPM. That's precise and accurate. And so back to this. When this reaches 6,000, we want this clock to stop counting. And so what we do is we take this value and we bring it all the way back here to the master clock. Oh, I'm sorry, not the master clock. We bring it all the way back to the reset pin. This is our reset signal. What that does is it brings this original chip back to Q0. When this goes to Q0, Q2 goes low. When Q2 goes low, this goes back to this clock and basically stops it from counting. And that is how we get this to stop. At the same time, what I did was I needed to find a way to also activate the latch and reset features of the CD40110 counters. And so what I did was, in addition, when Q2 went high, I wanted during that period while this is getting activated, I want this to be counting, but I don't want it to be, I don't want it to show how it's counting. And so what I did was I got a separate 555 timer, and I put a 555 timer in bistable mode. So every time Q2 went on, let's make it go that way. This was connected to pin 2, the 555 timer. If you look at the output of this, via pin 3, and then you have pin 4, which is the reset. So the way this works is reset is an active low. Q2 is basically connected via a resistor to VCC, 20K resistor. Okay, so this is always high. What I did to the Q2 signal is through another inverter, I would make this ground pin 2. When it would ground pin 2 by sending a low pulse to pin 2, this would go on. And then every time this Q2 would go low again, I would connect it to this and send the grounding signal to the reset, and then this would go high. And so what this basically did, it was during the Q2 phase of the signal, it would give you a pulse. And this was only during the Q2 period. And so what this pulse did was every time it would go off, the falling edge of it would be attached to the latch pin. And then after a short delay through a 0.1 microfarad capacitor and a 1K resistor to ground, this would go to the reset. And so as soon as this would stop counting, this value was latched, and then the value in the counters was reset. So it would still display the latched value, but it would reset this counter in preparation for the next count. So you wouldn't actively see it counting the entire time. Otherwise, it would count completely. Also, when this value went back to Q0, at Q0, I basically took the Q0 signal and also through a capacitor, 0.1 microfarad, and a resistor tied to ground. This would turn this signal into a differentiator, so a short burst signal instead of the whole time Q0 was high. And I would attach that to preset enable. Of the first set of counters. This first set of counters requires a short burst, a short pulse for preset enable, and that will, and since the inputs are connected to ground, that reset the period counter, which would then restart counting when this went to Q1 again. So basically, the entire timing diagram kind of looks like this, where this is the Hall sensor signal, and Q0 is high at first because that's where the starting point is. The minute the first Hall sensor signal comes, Q0 goes low and Q1 comes on. Q1 stays on, and this is the period counting time. Q1 stays on until the next signal from the Hall sensor goes on. At this point, Q1 goes low and Q2 goes on. Q2 is on for a fixed amount of time, basically 6,000/100ths of a second. Basically, at 18 kilohertz, it counts to 6,000 in 0.33 seconds. So Q2 is always on for 0.33 seconds. You can make it faster with a faster clock, but I wanted something that was going to start counting, finish counting before the next Hall sensor trigger would come. So something that's relatively quick. Using the 18 kilohertz clock, this will count to 6,000 in 0.33 seconds. And, you know, unless it's spinning really fast, the anemometer, 0.33 seconds is a reasonable amount of time. I can make it shorter than that by making it a 24 kilohertz clock or a 30 kilohertz clock, but 18 kilohertz seemed reasonable to me. So Q2 counts to 6,000 and then resets everything. And it resets everything in the middle, usually in the middle of a cycle, in the middle of a spinning period. And then this gets reset to Q0. This original chip gets reset to Q0. And at Q0, it waits. It basically waits for the next Hall sensor trigger to come. And when it comes, the cycle begins again. And when that happens, it starts the entire process and starts counting. And that is basically how you make a reciprocal frequency counter that is precise to a level of 1/100ths of a second. So you can make it more precise. You know, I think it seems like it's enough. Now, the last part of this, at least for the anemometer crowd, for the people who aren't interested in the anemometer but are more interested in the reciprocal frequency counter, you guys could stop watching. But for the anemometer part, the more exciting thing for me here is converting this value to miles per hour. And that's just math and dividing up the frequency. So, you know, if you take your anemometer, go back to my bad picture of the anemometer. Apparently, anemometer technology is, if I was going to draw the anemometer from a bird's eye view, this is a circle, basically, and it spins in whatever direction. And so you have your value of rotations per minute from the counter circuit on the other side. And so the way this works is you're measuring to the middle of the cup from the center, and that's your radius, right? And so a complete rotation is radius r times 2 pi, and that's your distance traveled per rotation. So one rotation is 2 pi r rotations, right? So if you have 2 pi r as your distance in whatever value you used, I used inches, you could use centimeters, whatever you want, 2 pi r, and that unit is inches. And you want to get this to miles per hour, so you have times 1 RPM, 1 rotation per minute per 2 pi r, okay? So times, let's say, X rotations per minute. So now you want to convert that into 12 inches per foot times 5280 feet per mile. To rearrange these values by taking reciprocals, and you basically have a value of 2 pi r over 12 times 60 over 5280. Okay? This value depends on your radius, and this is what the multiplier of the RPM value is. So in my case, plus with anemometers, there's also a little fudge factor, which is usually 3 to 5. Depends on the size of the anemometer. If you have a store-bought anemometer, you get a fudge factor that's calculates out based on friction and friction of rotation and wind resistance to the opposite. So basically it has to be calibrated. And so when I calibrated, my fudge factor was about 5. When I calibrated to basically known wind speed, and I repeatedly got the same value. So in my case, this is 5. Some cases it's 3, some cases it's 6, depends on the size and everything. So anyway, when you calculate all this out, for me, every RPM is 0.1 miles per hour. So 1 mile per hour is just basically a tenth of the RPM value. So 1 mile per hour or 1 RPM, equals 0.1 mile per hour. Okay, so, sorry, complex math is getting, seems to be getting easier for me, but the simple stuff is getting crazy. Any case, so all you have to do in order to get from RPM to mile per hour in my case is multiply this value by 0.1, which, you could use in separate divide by 10 counter to do that, and change the value. But in my case, since I already had an LED display here and there's the decimal point, all I did was just turn on the decimal point, and which is connected to the G pin of the LED display, and with a separate little switch, and that basically takes the RPM value and puts a decimal point, shifts it 1 decimal point over, and that essentially does the 0.1 for me. For other folks, you might have to use an actual frequency divider, which is fairly easy because you just take this frequency and just put it through any kind of frequency counter to divide it. So you divide by 2, divide by 3, divide by 10, whatever you want. And whatever your factor is going to be. Mine just happened to be lucky-ish. It was actually 0.103 or something like that for when I calculate my final factor. But, I don't need that level of accuracy. 0.1 will suffice, and it seemed to work well for me. But anyway, that is how I made a anemometer circuit based on a reciprocal frequency counter that is accurate to 0.01 seconds. If anybody has a question or wants to see the final schematic, I think my schematic is basically the same thing. It's just this. I have a little, you can change up values of different resistors here and there because I have little light indicators at every point in this circuit, little LED light indicators, more to make sure things were working as I progressed through them. And so I have a little LED here every time there's a positive pulse, so I know when it's coming. And this is going to ground, and then this is the true clock signal. Be careful with using values of resistors that are too low here, because the LED lights up bright, but then there's not enough voltage to trigger the clock signal of the counter. So I used a 2K resistor for every LED, and that seemed to work pretty well. Same thing here. I had an LED on this, so I could see this gating. I had an LED for the output of the 18 kilohertz clock. I have an LED for the 100 hertz clock. So pretty much a whole ton of LEDs just to indicate that things are working well, and at each step of the way. Mainly in case things stop working, I could tell where by where the LED is not turning on, that's where the problem is. But in any case, please don't hesitate to get in touch with me, ask me questions, leave me comments. If you think this is all crazy, tell me that too. But in any case, thank you for watching, and onward to new adventures.